All right, it's Friday afternoon. We're continuing with stellar evolution. Okay, we left off with a star reaching to the main sequence. I think it was stage number 7. Right? And on the main sequence, right, the stars they pulled in enough matter, there's enough gravity, the core has gotten hot enough to 15 million degrees Kelvin, right, and starting helium fusion. And in helium fusion, on the main sequence, the internal pressure of gravity is balanced against the outward pressure from the nuclear fusion. So we've got the balance of forces. So the stars are in a perfect sphere, perfectly balanced, and consuming hydrogen, producing helium. When the stars start running out of hydrogen, right, this is when the star gets out of balance. Once the star is out of balance, its structure changes. So, main sequence stars slowly fusing helium into hydrogen in the core. We call this the core hydrogen burn. And a main sequence star is in that balance, right? That hydrostatic equilibrium. Outward pressure and inward pressure of gravity are balanced. But eventually, hydrogen is going to be used up, and you're going to lose that internal balance. And I spelled exhausted wrong there. And when you lose that internal balance, the structure and the appearance of the star is going to change, and the star leaves the main sequence on the Hertzsprung-Russell diagram and starts moving towards the red giant phase. And depending on the star, it might become a super red giant. But what happens to a star after the main sequence depends on how big the star is. You typically sun mass stars, so stars similar to our sun, they become white dwarfs and planetary nebula, which we'll talk about soon. Right? Larger stars, they go supernova and there's a neutron star left behind. And the supermassive stars, they go super or hypernova and they leave a black hole behind. So post main sequence events depends on the star mass. Low mass stars, less than 8 solar masses, so 8 times our sun, die gently, right? Whereas high mass stars, more than 8 solar masses, die catastrophically. So this is gently drifting off into a planetary nebula, leaving a white dwarf behind, whereas catastrophically, an explosion, so a nova, supernova or hypernova, and leaving behind either a neutron star or a black hole. So, in a star like ours, after about 10 billion years of steady hydrogen core burn, our sun will start to run out of fuel. So, our star should burn for about 10 billion years. Our star has already been burning for about 5. So, it's got half of its lifespan left. Let's move me over to here. Just going to hang out in this corner now. So we reach the sub giant phase. Okay, got an itchy ear. So let's look at this graph here first of all. When we have a star at birth, in the core it's hydrogen, and around the core is the helium that was produced from nuclear fusion. Okay. And then as more time passes, you can see that the quantity of hydrogen decreases and you're seeing more helium in the core, right? And as so this was like 5 billion years, 10 billion years. If you look at the core, there's very little hydrogen and it's mostly helium. Around the core though, so let me explain this diagram a little better. From here to the dashed line is the core. Okay? So at birth, the core is like 90% hydrogen, 10% helium. And as hydrogen gets fused into helium, 5 billion years later, we look at the core and we're seeing more and more helium in the core and less hydrogen. 10 billion years, very little hydrogen and lots of helium. Outside of the core, though, we still see a high concentration of hydrogen. So, as hydrogen is fused into helium, the helium content of the star increases fastest at the core where the temperature is the highest. Right? This is where we have high temperatures, we have nuclear fusion. The inner helium-rich region becomes larger and more deficient, I spelled that wrong, in hydrogen as the star continues to burn. So the core, we have less hydrogen, more helium. Outward gas pressure, so the pushing outwards, decreases in the hydrogen core. So the outward pressure of nuclear fusion is decreasing because nuclear fusion is slowing down. There's less fuel. But all that mass is still there. So the gravity is pushing in. Right? Before they were balanced, right? Before we had balance outward, balance inward. But as the hydrogen builds up and as the helium builds up and there's less hydrogen in the core, hydrogen fusion, the hydrogen core burn is slowing down. So now there's less outward pressure to compensate for the gravitational pressure pulling inwards. Sorry, my nose is all plugged up. So the outward gas pressure decreases in the helium core. So the core is mostly helium, but the inward gravity continues to push inwards. So it squeezes the inner core. The inner core is being compacted. Gravity is pulling everything in because there's less pressure. So what happens is that hydrogen core gets compressed and compressed and compressed, and it starts getting hotter and hotter and hotter. So we increase the temperature of the core, right? So the core gets really hot, and the hydrogen gas that surrounds the core starts fusing. Okay, so we get nuclear fusion then around the core. Nuclear fusion isn't really happening at the helium core right now, right? But it's nuclear fusion is happening around the core. We have what's called the hydrogen shell burn. So one more time, the core fusion slowed down because it's become mostly helium. It's compressed and gotten hotter and hotter and hotter. It's gotten so hot because the gravity squeezed it all in because the outward pressure dropped. So the core got compressed. It got hotter and hotter and hotter that it could start fusing the hydrogen gas that surrounds the core. So we then get the hydrogen shell burn. And the hydrogen shell burn generates energy faster than the main sequence core. So the temperature is so high that the shell burning around the hydrogen is so hot that it's happening super fast. So as the core keeps on shrinking due to gravity pulling it inwards, because there's so much gravity pulling in and there's less and less hydrogen, it gets hotter and hotter and hotter, right? So we get more and more hydrogen shell burn, right? So there's more energy being produced in the star, and the star's luminosity, the amount of energy it releases, increases. So this part is the subgiant branch. This is what's happening when we're on the main sequence. We run out of hydrogen. Right, the core is mostly helium. Gravity overcomes the outward pressure. The core compresses, becomes super hot. It starts fusing the hydrogen around the core. And we have hydrogen shell burn, which happens faster than the core burn, and we increase the brightness of the star. So let's look at this diagram here of a star. We've got the hydrogen core, burning in the center. Okay. That hydrogen burning core makes helium. The core becomes helium. Okay. that helium really isn't fusing at this point. So gravity is pulling all that mass inwards. As it pulls it inwards, it gets super hot. Right? As it gets super hot, it starts burning the hydrogen around the core in the hydrogen shell burn. It increases the brightness of the star, but we're having more energy production, and that actually causes the star to start to expand, to swell outwards on its way to becoming a giant star. And here we've called it an expanding subgiant. So, because the star has expanded, right, that energy is being spread out over a larger area. The surface cools, but its radius has increased, right? So it's gotten larger. So the surface is cooled, but the star is larger, so it's becoming more luminous. So here we have the main sequence star at stage 7, and we're now in the subgiant branch here, where the star's luminosity is a little higher, it's gotten slightly brighter, but the star is getting bigger and bigger. Okay, I just need to pause. My class is going to start soon, so I will resume this after I'm done teaching my grade 9s. Okay, so let's resume. Class is now finished. It's around 3 o'clock. So the the hydrogen core is all but expended. Starts to collapse under gravity, gets really hot, starts burning hydrogen in the shell around the core. Like that energy, it's really, really hot. It's burning extremely hot, and that causes the star to expand. So that's the subgiant phase. We enter the red giant phase. The helium core is unbalanced and shrinking, so gravity's pulling it inwards. The outward pressure at the core isn't that great. Hydrogen shell burn is fusing hydrogen into helium at an increased rate because the core is collapsing and getting hotter and hotter. The gas pressure produced by the enhanced shell burn, so outside of the core, that hydrogen is burning, right? And it's causing, right, so that burn and the pressure is pushing outwards on the rest of the star that is not going through fusion. So you've got the core of the star. Outside the core, you've got like the radiative layer and the convective layer and then the photosphere. Those parts aren't burning per se. When I say burn, they're not going through nuclear fusion. So that outward pressure from the fusion happening in the hydrogen shell is pushing out those outer layers. So it's making the star get bigger. The core is still collapsing under gravity, but that hydrogen shell is pushing outwards. Okay, and as it's pushing outwards, the star is expanding, getting bigger, but it's cooling. Right? Those outer layers are cooling. So we've gone from the main sequence to now a big red giant. Right? The shell burn is shrinking the core. The shell burn in the shrinking core is so intense that the giant's luminosity may increase hundreds of times, and its radius is also increased 100-fold. And this core at the center of the star, made of helium, is now extremely dense. Next stage, stage 10. Let's find a spot for me. So now we've gone into the red giant phase, but gravity is still compressing that core, so we hit helium fusion. In stars less than a quarter mass of the sun, the unbalanced forces tear the star apart, causing the core to collapse, and the rest of the star will drift away as a planetary nebula. So in small stars, right, the outer layers will still keep expanding and push away from the star, becoming that planetary nebula, leaving a dwarf star at the center. So that shell burn pushes everything away. Slightly larger stars, like stars the size of our sun, they do something different. That collapsing core, it gets hot enough eventually that it starts fusing helium into a heavier element, and that heavier element is carbon. So we have helium fusing with helium. It produces beryllium and radiation, gamma rays. And that pressure still can then fuse helium and beryllium together to make carbon. So we're starting to produce heavier elements at the core. Still into the helium fusion phase, we then get what's called, I gotta find a good spot for me, the we get the helium flash. Okay, so let's read along here. To understand, we must first explain thermal pressure. As a star heats up, thermal pressure causes the core to expand, and as a result of expansion, it's going to keep cool. Right, so it's going to cool as it expands. So we end up with a balance. We get this with this balance between pressure and gravity. In stars that are comparable mass to the sun, something remarkable happens. The helium gas will enter a new state of matter governed by quantum mechanics. So this is high level physics. So at this point, the core enters the degeneracy phase, where electrons are taken away from the nuclei by the intense heat of the reaction of the fusion in the core. So in the core, the pressure isn't resisting gravity anymore. Sorry, the pressure resisting gravity isn't thermal anymore. It's all those electrons. It's called electron degeneracy. This has nothing to do with temperature anymore. In a star supported by thermal pressure, the increase in the temperature produced by helium fusion would lead to an increase in thermal pressure. The gases would expand and cool. Right? As they cool, it reduces burning rate and the star reaches balance. When we get super hot, when we reach the electron degenerate core, pressure and temperature are no longer tied together. We end up with like a runaway reaction. So helium fusion starts. There is no rise in pressure. There's no expansion at this point. There's no cooling. Right? Temperature goes up, the star should expand. But at this phase, it's getting hotter and hotter, but there's no expansion. So it just gets hotter and hotter and hotter. We have this runaway reaction that we call the helium flash. So this helium flash is extremely brief, but when it happens, it releases a tremendous amount of energy. Very briefly, only for a few seconds, but there's a tremendous release of energy during the helium flash. Right? Everything gets super, super hot, right? And then thermal pressure becomes dominant again, and then the star starts to expand again and cool. So we end up redeveloping a balance between pressure and gravity. And don't worry so much about the nitty gritty of the helium flash. Just know that it happens. And we end up developing the stable core that is now fusing hydrogen into carbon. So being at the stable point, the star enters what's called the horizontal branch of the HR diagram. It should be on the next slide here. Right here, the horizontal branch, where the star is relatively stable for quite a period of time at this horizontal branch. You get a spike in luminosity for the helium flash, then things stabilize, and the star is in the horizontal branch where we'd find our red giants. So where it is in the horizontal branch is determined by how big the star is. Right? Bigger stars, moving away here, bigger stars would tend to be hotter, right? So they'd probably be further along in the temperature scale towards the hotter temperatures, where smaller stars would be further towards the right of this line. So a star's position on the horizontal branch is determined by its mass, right? Whatever remains after it becomes a red giant. When we're a red giant, everything is really, really turbulent. The outer layers of the star, right, they can be pushed away by the energy of the core, by the energy of the shell burn. That shell burn, right, can start pushing away at the fabric of the star, and the star can eject large portions of its mass when it's a red giant. So the red giant star isn't stable. Big chunks of the star can be blown away by that internal pressure that's going on. So we look at the core now, right? We've got the non-burning part of the star, but it's still super hot. Right? And what started as a hydrogen core became a helium core, and then the helium core got fused into carbon. So at the center of the star, we have carbon ash. The carbon is not burning. It's not hot enough to fuse carbon. Around that carbon, you got a shell of helium, and around that helium, you got a shell of burning hydrogen. And that's where we'll leave it. Right? We'll get into the rest. Right? So we're at the red giant. We're going to get into phases, what happens after the red giant. Don't stress about the helium flash and the electron degeneracy. Just know the helium flash happens. Right? And we're still putting all these pieces together. After Monday or Tuesday, you should be able to put all these pieces together and explain the evolution of a star in detail. Okay, I'm going to stop it here.